Okay, so in the last lecture, we talked about the idea that if you have more than one chiral center, you have a new potential stereochemical relationship. You still have an enantiomeric relationships where the two molecules are mirror images of each other. And we know that they're mirror images because every single chiral center is reversed in the two molecules. So if you have the two S centers of this molecule, its enantiomer would have two R stereocenters. So that was a second type of stereochemical relationship that we had from enantiomers to diastereomers, where at least one chiral center has the same configuration and at least one chiral center has opposite configuration. The third type of stereochemical relationship is what's called a meso compound. And the best way to illustrate this is to simply draw two stereocenters, and I'll do this in a Fischer projection. So how about I put a chlorine here, an H here, we'll put a chlorine there, we'll put an H there, and then we'll put two methyl groups on the top and bottom. So we'll go ahead and make molecule A. And now I'm going to go ahead and draw the enantiomer to molecule A. I'm going to draw its mirror image. So I'm still going to have my methyl groups on the top and bottom. Now I'm going to have my chlorine here, my hydrogen there, and my chlorine over here, and my H there. So those two molecules, A and B, are now enantiomers, because they're mirror images and they're not superimposable. Or sorry, they are superimposable. So now let's draw a diastereomer to molecule A. So how about I keep the top chiral center in the same configuration, and I'll reverse the bottom chiral center. So I'll take the top chiral center, keep the chlorine on the left, but now I'll reverse or invert the chiral center, the bottom chiral center here in molecule A. And to do that, I'm just going to replace or switch the Cl and the H. So if I switch those two groups once, I'm going to invert that chiral center, or change it from R to S or S to R. Okay, so molecule C here is a diastereomer to both molecules A and B. And now let's draw the mirror image of molecule C. So if I do that, I get what I'm going to call molecule D. Now here's the problem between molecules C and D. These two mirror images are actually superimposable. So C and D are going to be superimposable mirror image isomers. Now that's something that we haven't encountered before. We said enantiomers were non-superimposable mirror image isomers, but now C and D are superimposable. And you might say, well, how are C and D superimposable? Well, if I took C and D and I rotated the entire molecule 180 degrees, okay, so I rotate this CH3 to the top, this CH3 up here to the bottom, the two Cl's would come over on the left-hand side, the H's would go on the right. So if I rotate that molecule 180 degrees, I would get this representation. And so, as you can see, C and D then are superimposable on each other. But yet they have chiral centers. So this is an example of the third type of stereochemical relationship that we have. C and D, although they're the same molecule. That's called a meso compound. And so what is a meso compound? Well, there's lots of ways to define it, but a meso compound has at least two chiral centers, or at least two chiral carbons, and is superimposable on its mirror image. That's the definition of a meso compound. So as you can see, compounds, or the C and D representation here, have two chiral centers. But it is superimposable on its mirror image. And what does that really mean? Well, what it means is a meso compound is overall not chiral. And that means that it does not rotate plane polarized light. Okay, any molecule that is superimposable on its mirror image is not chiral. It doesn't have the ability to exist in a left and a right-handed form. And so therefore, it's not chiral. It doesn't rotate plane polarized light. Now, another possible way to define meso is to say that a meso is a compound that has chiral centers, but it also has an internal mirror plane of symmetry. Now, before we talked about internal mirror planes of symmetry cutting through carbons, and the carbons that it cut through, those carbons were no longer chiral. Can you draw the mirror plane of symmetry through this molecule, and that mirror plane does not cut through the chiral centers? Well, if you draw your mirror plane this way, it cuts through the molecule, does not cut through any chiral centers, and splits the molecule in half. So this would be the mirror plane that meso compound has. So meso is a new type of relationship, and actually we could say C and D. If we say C and D are meso compounds, we're actually that's wrong, because C and D are the same molecule. So it turns out that when we said before that you had 2 to the n possible stereoisomers, it turns out that that formula predicts the maximum number of possible stereoisomers. Because if you have the possibility to have a meso compound, then you'll have one less for each of those meso compounds. For instance, here we have 2 chiral centers, but we only have 3 different stereoisomers, since C and D are the same. Okay. So possible definitions for meso compound: it's a compound that has at least 2 chiral centers and is superimposable on its mirror image, or you can also say that it is a compound that has at least 2 chiral centers and an internal mirror plane of symmetry. Okay, so this molecule C is a meso compound. So how about we now go back and we look at some other molecules and try and determine, are they meso compounds? For instance, is this molecule a meso compound? Is this molecule a meso compound? Is that molecule a meso compound? Remember the definition. You have to have an internal mirror plane of symmetry, but you also have to have chiral centers. So let's call this molecule A. Is molecule A chiral or not? if you said, or sorry, meso or not. If you said that A is a meso compound, you are correct. It does have two chiral centers, and it does have a mirror plane that cuts the molecule in half. How about B? Is B meso? If you said yes, it also has two chiral centers and a mirror plane that cuts the molecule in half. How about C? Is C meso? C is not meso, because the mirror plane cuts through the two carbons, and so therefore it has no chiral carbons, and the basic definition of a meso compound is you have to have at least two chiral centers. C has none, therefore C is not meso. Is molecule D meso? It has two chiral centers, but no internal mirror plane, therefore it's not meso. Okay, so there are many different molecules that we can have that are meso, and so the question is, do they have chiral centers? Do they have the internal mirror plane of symmetry? Now, either way, if you have a meso compound, the meso compound has 0 degrees of rotation. It does not rotate plane polarized light. Because it's superimposable on its mirror image, therefore meso compounds aren't chiral. Okay. Now, that's an important that's the third and final type of stereoisomer that we're going to have. Now what we're going to do is now we're going to focus on, if I give you two molecules, can you tell me whether those molecules are the same? Are they the same meso compound? Are they enantiomers of each other? Or are they diastereomers of each other? And so let's look at a couple of examples and how we might approach this problem. So let's say I gave you two tetrahedral carbons, and I said, let's put a chlorine, a bromine, a methyl, and a hydrogen, and then I'll put the hydrogen, the bromine, the methyl group, and the chlorine there. What's the relationship between these two molecules? And again, your choices are, they are the same, and they're not meso. They are the same meso compounds. They are enantiomers of each other, or they're diastereomers. Okay. Now, how are you going to approach this problem? Well, for single chiral centers, you always have the option of determining R and S, and if they're both R and both S, they'd be the same. Since this only has one chiral center, it can't be meso. Right? Meso requires more than one chiral center. So you can always determine R and S and try and figure out whether the stereo centers are the same, opposite, maybe one same, one opposite, or both opposites. But that's kind of the hard way to do it, and you will miss meso compounds if you just determine R's and S. So another way to look at this molecule is simply try and make the right-hand molecule into the left-hand molecule or vice versa. So for instance, in this case, can I rotate the CH3s and the BRs? Can I turn the left-hand molecule into the right-hand molecule? And the answer is no, I can't, because the bromines are already matched up, as are the CH3s. And so therefore the chlorine and the hydrogens don't match up, so these two molecules then are enantiomers. Okay. Now, you could use our group switching method to try and turn the left hand into the right hand, and you can count the number of switches. Remember, every time you switch two groups an even number of times, that means that the chiral centers are the same. If you have to switch an odd number of times in order to make the left into the right, then what you'll find is that the chiral centers have opposite configuration. So looking at these two molecules, in order to make the left into the right, I would have to switch the H and the Cl. That would be one switch. Therefore, these two molecules have opposite configurations, and that's what the basic definition of enantiomers are. Enantiomers have each chiral carbon having the opposite configuration. So you can use the group switching and just keep track of how many switches it takes to go from the left to the right. If it's even, they're the same configuration. If it's an odd number, they're opposite configurations. Okay, let's try another one of these molecules then. Now with one chiral center, your choice is either they're enantiomers or the same and not meso. So is this one the same molecule or are they enantiomers of each other? And remember, they can't be diastereomers either because diastereomers require two or more chiral centers. Okay. Now if you wanted to use group switching, you could switch. How many switches are going to take to make the left into the right? Well, I'd have to switch the CH3 and the Cl, so that would be one switch. And then I'd have to switch the CH3 and the CH2CH3. So that means after two switches, now the molecules are lined up exactly the same, and so therefore these are the same molecule, and they're not meso because meso compounds require two or more chiral centers. Okay, so it took an even number of switches to get from left to right. Therefore, these two they basically have the same configuration. And so therefore, they're the same molecule. Now, we have to be careful when I draw the molecules in different orientations. For instance, let's say I gave you a Fischer projection and I gave you a just normal tetrahedral representation. So if I get when Cl, H, CH3, and Br, if I did this, if I gave you those two molecules, you either have to orient those two molecules the same, like they were given to you over here in these two problems, but if they're not in the same orientation, then generally what you have to do is you have no choice but to go and to determine the R and the S configurations directly and see whether they're the same or not. So in this case, looking at my groups, I'd have group 1, group 2, group 3, and group 4. And remember that the Fischer projection has a bow tie structure, so that means I've got a 4, a 3, a 2, and a 1. And so if I'm going to I either group switch between 4 and 2 and 1 and 3, or I might grab number 1 and rotate 3 into 4, 4 into 2, and 2 into 3 to determine whether this is R or S. So 1 didn't move, my 4 is now here, my 2 is here, my 3 is there. Going from 1 to 2 to 3, this is the R. What is this one over here? 1, 2, 3, 4. 4 is pointing away from me. So in this case, these also are the same molecules and they are not meso. Okay, so if the two molecules are in different orientations, you really have two choices. Either put them in the same orientation and then you can group switch or compare, or the other thing is just determine R and S. If they're the same configuration, they're the same molecule. If they're opposite configurations, then they're enantiomers. Okay, so that's a couple of examples of doing a single chiral center. What if we have Fischer projections? So let's say I give you two molecules here, put a chlorine, an H, a Br, an OH, about a CH3, and another H. So up here I'll put an H, Br, Cl, and then my H, OH, CH3. So what are these two molecules? Now, since these molecules have more than one chiral center, your choices are now still going to be same, and they're not meso. The same meso compound in enantiomers of each other, or D, they're diastereomers. Okay. Those are going to be your choices. So looking at this, the first thing that we have to do is make sure that the molecules are actually that I'm comparing two carbons that have the same groups attached to it. And I'll show you what that means here in a minute. So in this case, the top carbon has bromine, chlorine, hydrogen. So the two top carbons are the same and the two bottom carbons are the same. Now I'm going to compare each chiral carbon differently or independently. So I'm going to look at the two top carbons and see whether they're the same or opposite configurations, and I'm going to look at the two bottom chiral carbons and determine whether they are the same or opposite configurations. And then if they both have opposite configurations, they would be enantiomers. If they both have the same configuration, they would be the same molecule and not meso, and I'll come back to that in a moment. And if one has the same configuration and one has the opposite configuration, then they fit our definition of diastereomers. Okay. Now, whenever I see a molecule with two chiral centers, the first thing I like to do is to see whether or not meso is a possibility. Now, when will meso be a possibility? When the two carbons, the two chiral carbons, have exactly the same three groups attached to them. But that's not the case here. Hydrogen, chlorine, bromine, those three groups are different than OH, CH3, and H. So there's no way to draw a mirror plane of symmetry in this molecule because these two carbons do not have the same groups attached to them. So therefore meso is not a possibility, which means over here that B is not a possibility for this molecule. So with that out of the way, what's the top carbon? Are the two top carbons, do they have the same configuration or do they have opposite configurations? Well, we could do group switching. I could switch the H and the Cl. So I did one switch, and now I'd have to switch the Cl and the Br. So it took me two switches to make the left into the right. Therefore, the top carbon has the same configuration in both molecules. For the bottom, what are these two? Are they the same configuration or are they opposite configurations? Well, if I'm going to match these up, I'm going to, let's see, switch my H and my CH3. So that's one switch. And then I'd have to switch the H and the OH for a second switch in order to get the left matching up with the right. That's an even number of switches, which means the bottom molecule also has the same configuration, the bottom chiral carbon. So in this case, both chiral carbons have the same configuration. Therefore, this molecule is, it is the same molecule, but it is not meso. Okay. Now let's look at a molecule where there is the possibility of meso. So how about I put how about these two molecules? Now when I look at this problem, the first thing I see is I see two chiral centers, and I see these two chiral centers each of them having a chlorine, hydrogen, and an OH group. So therefore, I immediately think, okay, these could be meso compounds, or they have the possibility of being meso compounds. Now, the only way I'm going to show that they are both meso compounds is to orient these molecules so that I can see the mirror plane that would cut through the center of the molecule like this. So how do you do that? Well, in a Fischer projection, what you have to realize is the half of the Fischer projection looks like this. That's kind of like your Newman projection on N. So you can rotate the three groups like this, holding the carbon in the plane of the screen constant. So it's very easy to rotate around a Fischer projection. If I wanted to, I could do that for this top molecule, for the top carbon and the bottom carbon. So for instance, let's say that I rotate my chlorine over here, my OH over here, and my H up here. Now the chlorines match up, but the H's and the OH's don't, so therefore this molecule is not meso. Okay, there's no way to come up with the mirror plane between the top and the bottom carbon. Now how about over here? Is this compound meso? Well, if I rotate this hydrogen down here, and I rotate this OH to the right, and I rotate the Cl over here, what do you see? You see the OHs now match up, the hydrogens now match up, and the two chlorines match up. Therefore, there's a mirror plane. So therefore, that molecule is meso. So the right molecule was meso, but the left molecule is not meso. Now remember, what's the original question? The original question is, what's the relationship between these two molecules? Well, if they were both meso, then you would have A, the same, or B, they're the same meso compound. But in this case, they're not. So what's the relationship between a meso and the other stereoisomer that is not the meso form? Well, let me just rewrite this after I did that rotation to make it a little bit clearer. Okay, so this is after I rotated around the top carbon for the left molecule, and for the right molecule, I'll put in what I wrote for the bottom carbon. So here clearly showing the meso. Okay, what's the relationship between these two molecules? Well, I still have to determine, I have to look at the top carbons, compare them. Are they the same or opposite configurations? How about the bottom carbon? Is it have the same or the opposite configurations? Now, the interesting thing here is that look at the top carbon. Let's just examine the top carbon. Without doing anything, can you tell me whether those two carbons have the same configuration or opposite configurations? Well, when I look at these two molecules, what do I see about the top carbons? I see that the top carbons are mirror images of each other. So what does that make their configuration? That makes the configurations opposite because they are mirror images of each other. Now when I look at the bottom carbons, I don't see those being mirror images. And so what I can do is I can do my group switching to try and turn left into right and see, does it take an even or odd number of switches? But I want to do this a little differently here to kind of show you that if the two chiral centers aren't mirror images of each other, could you make them so that they matched up, so they had exactly the same configuration? Well, if you notice in this molecule, if I rotate my Cl over here, my OH down here, and my H up here, notice that my OH, my two OHs match up, my two Cl's now match up, both on the right-hand side, and my two H's match up on the left-hand side. So that bottom carbon looks like this. It's got After this rotation, I've got a chlorine, an OH, and an H, and that matches up with a chlorine, an OH, and an H. So in this case, they have the same configuration. And so now I have a molecule that had two of the chiral centers had opposite configuration, two of the chiral centers had the same configuration. And so what does that make the relationship between these two? It makes them diastereomers. So actually, when you find that one of the molecules is the mesoform and the other's not the mesoform, you can actually immediately say those two are diastereomers of each other. Now, you have to actually physically look for this mirror plane of symmetry, because it's possible that these two molecules may be the same, not mesoform, which would make them the same and not meso. Okay, so whenever you have the possibility of the meso with the two chiral centers having the exact same groups attached to it, you have to rotate the molecule to see if the first molecule is meso or if the second molecule is meso. Okay, and so you have no choice but to manipulate those molecules, because you could, if they were the same meso compound, if you determined R and S, you'd find out they had the same configurations. And even if you did your group switching, you'd have the two carbons having the same configuration. But you might say, well, they're the same, but you don't know if they're the same because they're the same meso compound, they're both meso, or they're the same and they're not meso. So you have to rotate these groups, and you have to physically see whether you see the mirror plane or not. Okay. So there's a couple of examples of the Fischer projections. We have to compare each carbon to determine whether they have the same or opposite configurations, remembering the definition that in enantiomers, every chiral center would have the opposite configuration, and in a pair of diastereomers, at least one would have the same configuration, and at least one would have opposite configuration. And with the same meso or same not meso is going to depend if you don't have the same three groups attached to a chiral carbon, to each of the two chiral carbons, there's no way it can be meso. If you do have the same three groups, then you have to check and see, are they both the same meso compound or not? There are other structures we can look at. We can look at Newman projections and say, okay, for a Newman projection, let's say I put a CH3 here, an OH here, a Cl there. How about a Cl here, a Br there, and an H there? Okay. And now let's say over here I have my OH, my Cl, and my CH3, and here I've got my H, my Br, and my Cl. There's two chiral centers in this molecule. Are these the same? And they're not meso? Are they the same meso compound? Are they enantiomers or are they diastereomers? Well, looking at these two Newman projections, first thing I do is I compare the groups that are attached to the front carbon versus the groups that are attached to the back carbon. Can either of these two molecules be meso? No, because the front carbon's got a methyl, OH, and Cl, and the back carbon's got a Cl, Br, and H. They don't have the same three groups attached. So now we have to compare front carbon to back carbon. Front carbons, are they the same configuration? Back carbons, are they the same or opposite configurations? Now you might say, do I have to put this in the Fischer projection? No. We can compare the front carbons as they stand now. So one of two things is going to happen. Either these front carbons are going to be mirror images of each other, or they're going to have the same orientation. And if you don't like that, group switch. So for instance, if I look at the front carbon, I see the Cl is in the same position. In order to turn the left carbon into the right carbon, what am I going to have to do? I'm going to have to switch the CH3 and the OH group. So for the front carbon, I did one switch. What does that mean? That means the front carbon, they have opposite configurations. How about the back carbon? Does the back carbon have the same configuration or opposite configurations? Well, you could group switch to try and line up the back carbon, the Cl, the Br, and the H. But let me do a rotation here. Because if I rotate this Br up here, and then I rotate this Cl over here, and then I rotate this H down here, looking at the H, the Cl, and the Br, what's the back carbon now? Can you see that the back carbon now has the mirror image? These are two mirror images of each other. So the bromine is here, the chlorines, and the H. So the back carbon, they have opposite configurations as well, because I can orient them to be mirror images of each other. If they were the same orientation, they'd be the same configuration. So now I have a molecule that has both carbons having opposite configurations. So what's the relationship between these two molecules? They are enantiomers. Okay. Now, you could say, how about two chairs? What's the relationship between these two molecules? Are they the same? And they're not meso? Are they the same meso compound? Are they enantiomers or are they diastereomers? Well, if I look at the two chiral centers, does the two chiral centers have the same groups attached to them? No. So therefore there's no way to pass a mirror plane through the molecule, so they're not meso. How about this carbon right here, the carbon with the chlorine? Same or opposite configuration in the two structures? If you said opposite, you're correct. Why? Because I just have to switch the Cl and the H once. How about these two chiral carbons? Do they have the same configuration or opposite configurations? If you said same, you're right. So now we have one chiral center having opposite configuration, one chiral center having the same configuration. What's the relationship between these two molecules? They are diastereomers. Okay. Now, one of the things you have to be careful of in these molecules is that you're always comparing the two structures. You're comparing the equivalent chiral centers. Because while you would call this a trick question, I don't. What if I gave you these two molecules and said, what is their relationship? Well, first thing I again look for is meso. These two molecules do not have the ability to be meso. So, and why? Because the top chiral center here has an HClOH, the bottom chiral center has a BrCH3. They don't have the same three groups attached. But now as I'm looking at this, I'm thinking, well, this top carbon here is the bottom carbon over here, and the bottom carbon over here is the top carbon over here. So I don't have the molecules in the same orientation. So worst comes to worst, I could always determine R and S on each one of those two chiral centers and compare whether the top carbon and the bottom carbon here has the R or S configuration and vice versa. But what I like to do is I'd like to just compare them visually. So what I have to do is put them in the same orientation, which means I'm going to have to take this molecule and I'm going to have to rotate it 180 degrees in order to make the bottom carbon into the top carbon. So now if I do that, what's going to happen? Well, my Cl is going to come up here. My OH was on the right-hand side, and now my OH is going to be on the left. My H is going to be on the right-hand side. For the top carbon, it now becomes the bottom carbon, so the H is there. My CH3 that was on the left side was on the right side goes to the left side, and the Br that was on the right side was on the left side goes to the right side. Okay, so now I've rotated these molecules so that the top carbons now match up so I can make a visual comparison. So if I look at the top carbons here, do they have the same configuration or opposite configurations? They have the opposite configuration. And you may say, how do you get that answer so fast? Well, because again, when I look at these two carbons, I see a mirror plane between this top carbon and this top carbon, so they're mirror images of each other, which means they have the opposite configuration. Now, when I look at the bottom carbon, I don't see any. I see that I'm going to either have to do group switching or I'm going to have to move the groups around. So with this molecule, what I see is that if I move the H up here and I move the Br over here, and then I move the CH3 down here, now looking at the Br, the CH3, and the H, the bottom carbon is in exactly the same configuration in both molecules. They're exactly the same. And so the bottom carbon has the same configuration. And so what's the relationship between these two molecules? They are diastereomers. One chiral carbon has the same configuration and one chiral carbon has opposite configuration. Okay. So this is the last topic in stereochemistry that we have to worry about, is how do we make our relationships, if given a pair of molecules, what is their relationship? And so you have to go through, and if you have just two chiral centers, you have to first see if the molecule could exist as meso or not. And then you have to, if there is the possibility of meso, then you have to determine, are they both meso? Are they both not meso? Or is one meso and one's not meso? And if one is and one isn't, that's easy. They're diastereomers. If they're both meso, then they're both the same meso compound. If they're both not meso, then you have to determine, are they the same or are they enantiomers of each other? Okay, so you don't necessarily have to always determine R and S configuration. That only happens when you have the molecules in different orientations. If the molecules can be placed in the same orientation, you can either switch groups and count the number of switches, even number of switches, same configuration, odd number, opposite, or you can look to see, are they mirror images of each other? Do they have the same orientation? Okay. So we're going to do some of these problems. You'll have some for the online quiz, and you'll have some for in class on Wednesday.